Everyone. Hope you are doing very well. Today we are going to see the theory part 9 of our chapter Haloalkanes and Haloarenes. So let's begin today's topic, that is NCERT chapter 6 Haloalkanes and Haloarenes, theory part 9, and specifically today we are going to focus on the section 6.7.1. This is disclaimer. The objective of today's lecture, so after attending this lecture, you will be able to correlate the structures of haloalkanes with the various type of reactions. Also, you will be able to appreciate the applications of organometallic compounds. So we will continue on these topics today. And if we talk about the topics that we covered today according to the NCERT, first of all, the section 6.7, chemical reactions, in which majorly we will cover the section 6.7.1, that is reactions of haloalkanes. And then we will also solve some examples, 6.7 and 6.8. So let's begin with the elimination reactions. So until now you have seen we have covered the SN1, the SN2 reactions, right? The substitution, nucleophilic, unimolecular and biomolecular reactions. And we have also covered the different stereochemical aspects of the substitution nucleophilic reactions. Today we are going to cover the elimination reactions. So first of all, let's see the conditions for the happening of the elimination reactions. First condition is there should be the presence of beta hydrogen in our reactant. Okay, so in our compound, in our reactant, beta hydrogen should be present. Beta hydrogen corresponding to the hydrogen which is present at the carbon, or you can say which is present at the adjacent carbon, adjacent to the carbon that is actually attaching with the functional group. Okay, or which is actually you can say carbocation. Okay, so the carbon which is carbocation and it is attaching with the carbon. If there is any hydrogen present in that carbon, that is considered as beta hydrogen. Okay, so there should be the presence of beta hydrogen. Second condition for the elimination reaction is there should be a base. Okay, in the reaction there should be a base for the donation of the electrons, which can act as nucleophile. And also there should be a presence of leaving group which can easily left from the reactions. So these are the three major conditions for the happening of the elimination reaction. First of all, there should be the presence of beta hydrogen. There should be base present which act as a nucleophile, and also there should be a leaving group. What are the cores for the elimination reaction? So first is, it should be, first step is the removal of beta hydrogen. Okay, so as per the condition, there should be a beta hydrogen so that we can remove it for the elimination reaction, right? So there is a elimination of, or there is a removal of beta hydrogen from the carbon. Secondly, the formation of pi bond. After the removal of beta hydrogen, there is a formation of pi bond involved. So pi bond means double bond. Okay, from which one of the bond is sigma and one of the bond is pi bond. So there is a formation of pi bond after the removal of beta hydrogen. And the third course for the elimination reaction is the departure of leaving group. The leaving group that is present, which we have studied as a condition, that leaving group should be present for the elimination reaction. So why? Because after the removal of beta hydrogen and the formation of pi bond, the leaving group should be leave, or you can say leaving group should be departure from our reaction, from our compound. Let's understand now the elimination reaction. When a haloalkane with the beta hydrogen atom is heated with an alcoholic solution of potassium hydroxide, alkene is formed. What we are saying? That when you have a haloalkane compound, when you have a haloalkane molecule, haloalkane means alkyl halide, in which there is a beta hydrogen atom. and you are heating that haloalkane with the alcoholic solution of potassium hydroxide. Then the product you are going to get is alkene. Alkene means the compound where there is the presence of double bond, the pi bond. So this is the elimination reaction happening where you can see that this halogen group, okay, or you can say the functional group, or you can say the substituent is present, or you can also call it as leaving group, because it have to leave, like for the elimination reaction to happen, for the alkene to form. So this leaving group, that is X, leave from here, from the alpha carbon. So the carbon to which the leaving group is attached is alpha carbon, and adjacent to that carbon is beta carbon, and the hydrogen which is bonding with this beta carbon is beta hydrogen atom. Okay, so what will happen? This beta hydrogen atom, the base, okay, the base act as a nucleophile and get this beta hydrogen atom, replace it, and the shared pair of electrons between the carbon and beta hydrogen atom will be, shift from a carbon hydrogen to carbon carbon bond, and the formation of pi bond happens, and this leaving group left from this alkyl halide haloalkane, and you will get your alkene as your final product, plus the base and the hydrogen, that is this as a side product, plus leaving group as an ion as a side product. Okay, so this is what elimination reaction happens through, that you should be having a beta hydrogen, you should have a base which can act as nucleophile, and you should have a leaving group in your compound, in your reactant, which is here as haloalkane, right? And what will happen? The nucleophile attacks on the beta hydrogen atom. The shared pair electrons between the carbon and hydrogen will shift from carbon hydrogen to carbon carbon to form the pi bond with the carbon, and this leaving group will left along with its charge. Okay, and you will get alkene as your major product after the formation of double bond or pi bond, plus BH, that is base and hydrogen combined together and eliminate as a side product, plus this X negative, that is the leaving group, will also be left. This reaction is also known as dehydrohalogenation reaction. Okay, because hydrogen and halogen both are leaving from the haloalkane, and you are getting an alkene as your product. So this reaction is also called as dehydrohalogenation reaction. In the elimination reaction, let's first of all talk about the Saytzeff's rule or Saytzeff's rule. Both are similar or both are same. Okay, what this rule says? This rule says that the elimination reactions happens and the more stable alkene is formed, which is as a major product. Okay, which is present as a major product. Okay, so after the elimination reaction, the more stable alkene you will got is your major product. This is what Saytzeff rule is saying. More stable alkene, how? Let's see. For example, you have this 2-bromopentane. Okay, pentane, because in your parent chain you have 5 carbon. At the second position you have bromine attached as a substituent. Okay, then what will happen? The bromine is attaching with the alpha carbon, which is our second carbon. So the beta hydrogen will be present at this first carbon and the third carbon, right? So hydroxyl group from your alcoholic potassium hydroxide, because we are talking about elimination reaction, right? So from the alcoholic potassium hydroxide, the base is OH minus. Okay, so the base is KOH, basically potassium hydroxide, from which we get a nucleophile, that is OH minus, which is going to attack on the beta hydrogen in our haloalkane, and the electrons will be shifted from the CH bond to CC bond to form the pi bond, right? So we have two possibilities, because we have 2 beta carbons here, the first carbon and the third carbon according to the numbering of the parent chain, right? So OH minus can attack on both the carbons, or you can say on both the hydrogen carbon. Okay, on both the hydrogen or beta hydrogens which is present on first and the third beta carbon. Okay, if the hydroxyl group that is our nucleophile, attacks on the first carbon beta hydrogen, you will get your product as pent-1-ene, that is pentene. Okay, pentene. So what will happen? This carbon hydrogen electrons will be moved or will be shifted from here to the carbon and form a pi bond, that is double bond, and this bromine will left from the reaction as a leaving group. Okay, so you will get a pentene, that means double bond at the first position, at the first carbon. Okay, this is only 19% of the product that you get. The other possibility is the hydroxyl group can attack on the other beta hydrogen present on other carbon, that is third carbon in the parent chain, right? So when this happens, that the hydroxyl group will attack on the beta hydrogen of the third carbon, then one of the hydrogen will be removed and the shared electrons will be shifted between the carbon, and the bromine will be left as a living ion or living group. Okay, and you will get your product as pent-2-ene. That means at the second position, at the second carbon in the parent chain, you will get a double bond or a pi bond. Okay, now this pent-2-ene you are getting is actually 81%. Okay, what does it mean? If you compare between the two alkenes mixture, or you can say alkene mixture, you are getting from which one alkene is only 19%, the other is 81%. Right? So this is the major product that you are getting, which is 81%, and this is the major product. That means this is more stable alkene. How? The more substituted carbon or the more substituted double bonded carbon atom is present in the compound, then it will be the major product. Okay, this is what the Saytzeff rule said. Okay, that if the product is having more substituted doubly bonded carbon, then that product is going to be our major product. That alkene is going to be the major product. So if you compare between the pent-1-ene and pent-2-ene, in the pent-1-ene, we have double bond between these two carbons, and only one carbon is having this much of propyl chain, okay, on it, and the other carbon have only two hydrogens on it, and the other two valencies are satisfying by this double bond. But in the pent-2-ene, you can see this one carbon is having ethyl group and the another carbon is attaching with the methyl group. Okay, so this is in this compound, in the pent-2-ene, the alkene, the double bonded carbon are more alkyl substituted or more substituted. That means this pent-2-ene will going to be the major product. Okay, so this product is more stable alkene, so this is our major product according to the Saytzeff's rule after the elimination reaction of the haloalkanes. Okay, or you can say 2-bromopentane. Let's see the competition between the substitution versus the elimination reaction. Okay, that means if you are we have until now talked about the substitution reaction, right? Now we will talk we have talked about elimination also, right? Substitution through SN1 and SN2, elimination through today we have seen according to the Saytzeff rules, right, in which elimination happens and the alkene we got as your major product. So let's see the competition between the substitution reaction and the elimination reaction. Okay, so let's understand this flow chart. So this is the flow chart for predicting the product, either through substitution or elimination, through which mechanism you are going to get your product. So let's start. First of all, we will look at the nucleophile. Okay, the process begin with your reactant, and reactant is basically your substrate, that is in this case haloalkanes, and your nucleophile, or you can also call it as base. Okay, so first step is that is the nucleophile or the base is strong. If it is yes, that means if the nucleophile or the base is a strong base, it has more tendency to donate its electrons, then it will go with the biomolecular reaction. Okay, so the reaction will happen and the reaction will be a biomolecular reaction. Biomolecular reaction means the reaction is happening where there is interaction or the collision between the reactants is happening. Okay, if the nucleophile or the base is not strong, if you are going with the no, Then we will look at what kind of substrate is present. Okay, the substrate means haloalkanes. What kind of substrate is present? Okay, if the substrate will be primary, so we have two conditions. First of all, our base is not strong. Okay, secondly, our substrate is also primary. Okay, that means in a single chain it is existing. So we got unfavorable reaction. That means no reaction will happen generally. Okay, so firstly we will understand through this yes process. So if our nucleophile or base is strong, yes, it is strong, then we will go through biomolecular reaction. We have two reactants reacting together. One is base, another is substrate. Okay, and our base is also strong, and reactant will collide with our base, to form the desired product. Okay, second step we will see is that is your nucleophile or base is bulky. We have a strong base, it's fine. Now we will go that is the nucleophile or your base is bulky. Bulky means is the nucleophile is tertiary. Okay, bulky means larger groups are attached with your base or surrounding the base. Okay, or basically the structure of the base is larger. So, is your nucleophile or base is bulky? You will see that, right? If you are going with the yes, that yes, it is bulky, then you are going with the elimination process. So, if your nucleophile or base is strong and also your nucleophile or base is bulky, then you will go with the elimination mechanism. Okay? So, if the nucleophile or base is not bulky, it is not bulky, then you will look upon that what kind of substrate is present at with you in the reaction. Okay, so firstly we will focus on the nucleophile. Okay, so and if nucleophile is corresponding to no, okay, then we will see at our substrate. Okay, so firstly we have started with the strong base, that if our base or nucleophile is strong, then we go with the biomolecular reaction. Then we will again see that if the nucleophile is bulky. Okay, if it is bulky, then we will go with the elimination mechanism, which we just have seen, where we are getting a unsaturated hydrocarbon as your product, as an alkene, right? But if your nucleophile or base is not bulky, then you will look at your substrate, your haloalkane, your reactant. Okay, so if your reactant is tertiary, then we again go with the elimination mechanism. Okay, tertiary reactant means you have your halogen attaching with the carbon with which is attaching with other 3 carbons. So this is a tertiary haloalkane, tertiary substrate you have. So you will go with the elimination reaction, elimination mechanism. If you go or if you have your substrate secondary means the halogen is attaching with the carbon that is attaching with other 2 carbons. So if the substrate is secondary, then it can majorly go with the elimination reaction, but based on the nature of your substrate and the nucleophile also, you can also go with the reaction, can also go with the SN2 mechanism. SN2 mechanism means substitution nucleophilic biomolecular, where the rate of the reaction is or the order of the reaction is 2. And the rate is depending upon the concentration of alkyl halide and the nucleophile you are using both, right? Now the third case is that if your substrate is primary or it is a methyl, just a methyl, CH4. Okay, so if your substrate is a methyl, that means CH3X, X is halogen. Okay, so if the substrate is methyl or either it is primary means your halogen is attaching with the carbon which is bonding with other 1 carbon. So if this is the case, then the product you will get is via SN2 mechanism, primarily through SN2 mechanism, the mechanism in which SN2 reactions happens, and there is a transition state happening, forming, right? Single step reaction is happening where no intermediate is forming. Rate is depending upon the concentration of alkyl halide and nucleophile both, remember? So if your substrate is primary, then you will go with the SN2 reaction, where your nucleophile is going to attack on the carbocation carbon from the opposite side of the carbon halogen bond, and stirring hindrance was the key factor there, right? Remember? So this is the case. Now let's move through the no direction. So if your nucleophile or base is not strong, then again you have seen that your nucleophile is not strong. Now you will look at your substrate. So if your substrate is a primary, so we have two bad conditions. So the first thing is your nucleophile is not strong base, and also your substrate is also primary. Then the unfavorable reaction will be happen. That means there will be no reaction generally. Okay. So this is the case. Now, unfavorable reaction means that the reaction is generally not likely to proceed. Other than primary, if your substrate is secondary, tertiary, or you can say stabilized primary, okay, then what will happen? You will get your reaction as a unimolecular. That means a single reactant will be there which is going to give you product, okay, after the reaction. So if your substrate is secondary or tertiary, in the case where your base is not strong, then the reaction will go in a unimolecular like way. So unimolecular reaction where only one molecule, where only one reactant will give you the product. Now, again you will look at your base for their bulkiness, right? Now, if your nucleophile or the base you are using in your reaction is bulky, if it is bulky, yes, it is bulky, then it will mostly be elimination reaction. It will show elimination reaction and give you your product, desired product. But if your base is not bulky, so it will go to SN1 reaction. The SN1 means substitution substitution nucleophilic unimolecular. Remember, where there are this SN1 mechanism is a two-step reaction where first step is the slowest step and rate determining step, right? And the formation of carbocation is also happening in the first step, and the rate of this reaction is only depending upon the concentration of alkyl halide. Remember? So if your nucleophile or base is not bulky, then the reaction will follow the SN1 mechanism and the substitution reaction will happen. Okay. So this is the flow chart which is predicting or helping you in predicting the product. Okay. So if you look upon the summary, basically the SN2 reaction, substitution reaction with the SN2 mechanism, the biomolecular substitution nucleophilic mechanism will follow or will favored by strong and non-bulky nucleophiles. Okay, strong. Okay, because in the strong, if your nucleophile is strong, then you are getting at the SN2 mechanism. Okay, so you are going to have your reaction mechanism as a substitution biomolecular mechanism. If the nucleophile is strong, if your base is strong, and the methyl or primary substrates are present. Okay, and the elimination reaction is going to be favored by the strong and also the bulky nucleophiles, okay, or the bases. And it also occurs mostly with the secondary and tertiary substrates. Okay, so if your substrate is secondary and tertiary and your nucleophile is bulky, your base is bulky, then the reaction will go via elimination reaction. Okay, SN2 reaction will go, the SN2 reaction will be happen, or this SN2 mechanism will be followed when your nucleophile or base is a strong base and your substrate is a primary or a methyl. Okay. Now, if you talk about the SN1, it will be favored by the, first of all, weak nucleophile or weak bases, and also the substrate is secondary, tertiary. Okay, or sometime your allylic or benzylic you can say stabilized primary substrate is also going to show you the SN1 mechanism reaction, the substitution reaction. Okay, an unfavorable reaction is shown by the weak nucleophiles or your weak bases with the primary substrate. That's the worst case, that's the bad case, okay, where there will be like no reaction. Okay, reaction is not likely to proceed. So this is the full flow chart where you can understand that if you are focusing on your nucleophile, if it is a if it is a reaction where reaction is happening between the substrate and your base, okay, then you can predict the product, whether the reaction mechanism is going to be elimination, SN2 or the SN1 reaction. Either reaction will happen through whether reaction will happen in one step or two step. You can predict that using this after understanding this flow chart. Okay, I hope you have understand that flow chart. If not, you can again go through that and you will definitely understand that. It was so easy. Okay, now let's talk about the reactions with metals. Reaction with magnesium. In the metals, we will talk about the magnesium. Okay, so in the reaction with the magnesium, which is actually the reaction involving the formation of Grignard reagent. You have listened this name of the reagent, Grignard reagent, a very lot. Okay, let's see what is it. Organometallic compound. So first of all, this reaction gives you a organometallic compound. Most organic chlorides, bromides and iodides react with certain metals to give the compounds that is containing the carbon metal bonds. Okay, so there are mostly chlorides, you can say organic chlorides, organic bromides and organic iodides that react with certain metals to give you the compounds that are containing the carbon and the metal bonds, the bond between carbon and metal. Haloalkanes or alkyl halides react with the magnesium metal in the dry ether to form alkyl magnesium halide or RMGX, which is also known as Grignard reagent. Okay, so this is what we called as Grignard reagent, the alkyl magnesium halide RMGX. And this forms when you react the haloalkanes with the magnesium metal in the dry ether. This is the reaction where we are getting, we are taking this ethyl bromide. This is a haloalkane. You are reacting this with magnesium metal in the presence of dry ether. And you are getting your product as Grignard reagent, that is CH3CH2 MgBr. The carbon and the magnesium bond here is covalent. That means the sharing of electrons is happening between the carbon and the magnesium. But also this bond is highly polar. So partial charges will be present at the carbon and the magnesium respectively. So this is the representation that the bond between the carbon, or you can say methyl, you can say alkyl group and the magnesium is highly polar, due to which this charged position is happening, partial negative and partial positive over the carbon and magnesium respectively. Also, there is partial negative charges at the halogen, because magnesium halogen bond is essentially ionic and halogen is electronegative. So it will get this partial negative charge. Grignard reagents are highly reactive and they react with any source of protons, either water, alcohols or amines, to give the hydrocarbons. So Grignard reagent reactivity is very high, and any source of proton means any molecule that can provide the proton, that can provide H positive in the reaction. With that source, the Grignard reagent is highly reactive. So like water provide H positive, alcohol can also provide H positive, amines can also provide the protons. So with these molecules, the Grignard reagents show the high reactivity to give you a hydrocarbon as your product. So if your Grignard reagent, if you added it with a proton source, that means either water, alcohol or amine, a molecule which provides you protons. So if you add it with the molecule which provides protons, you are going to get a hydrocarbon plus your side product as magnesium hydroxide halide. Because Grignard reagent is highly reactive towards the source of proton, that means towards the water molecule, okay, because it provides a proton to react with the Grignard reagent and form the hydrocarbon, okay. So the precaution you have to take is that it is very important you perform the reaction of Grignard reagent in the presence of dry ether, or you should use dry ether to avoid any trace of mixture, because Grignard reagent are extremely reactive towards the water molecule and any kind of moisture. So if there is any water, if there water is present, the Grignard reagent will immediately react with it and destroying the reagent and forming an alkane instead of allowing the intended reaction to occur, due to which we should avoid any trace of moisture while the reaction of Grignard reagent, and we should use dry ether. Second reaction is Wurtz reaction. Okay, so what is Wurtz reaction? Alkyl halides react with sodium metal, that is Na, okay, in the dry ether to give hydrocarbons which are containing double the number of carbon atoms present in the reactant, or you can say halide. Okay, so in the Wurtz reaction, what we do, basically we get the alkanes as your product, where the carbon number is double the carbon number which is actually present comparative to the in the reactant. Okay, so in the reactant, if there are 2 carbon present, in the product you will get your carbon number will increase from 2 to 4. It will double. Okay, so the Wurtz reaction synthesize alkanes. So the alkyl halides react via the reaction of alkyl halides with the sodium metal in the dry ether presence to give the hydrocarbons, the alkanes, which are containing double the number of carbon atoms comparative to the carbon atom present in your reactant. Here reactant is alkyl halide, because we are talking about haloalkanes, right? So you have to react 2 molecules of haloalkanes with the sodium metal to react, and you will get a hydrocarbon having double the number of carbon comparative to the alkyl halide, plus 2 NaX sodium halide you will get as your side product. Okay, so what will happening? Basically, sodium donate its electrons to the alkyl halide to form a alkyl halide radical. This reaction actually follows the radical mechanism, and the sodium donates its electron to the alkyl halide to form the alkyl halide mechanism, and sodium will form sodium halide, right? Also, the 2 alkyl halide radicals will combine together to form the alkane, that is R and R. Okay, that's why you are getting the number of carbon as double comparative to your halide. Let's see the example of this reaction. 2CH3CH2Br plus 2Na in the presence of dry ether. So in the presence of dry ether, you are reacting alkyl bromide, alkyl halide with the sodium metal. So you are taking 2 molecules of this ethyl bromide reacting with 2 sodium metals. In the presence of dry ether, the reaction is proceeding, and you are getting CH3, CH2, CH2, CH3, that is butane having 4 carbons in it plus 2 molecules of sodium bromide. Now this reaction is suitable for preparing symmetrical alkanes, because due to this fact that in your product you will get double number of the carbons comparative to your alkyl halide, this reaction is, or you can say Wurtz reaction is suitable if you want to prepare any symmetrical alkane. Okay, as you can see, your product will always be having a even number of carbons. Okay, 2, 4, 6. Okay, or you can also say you can create a symmetrical alkanes. How symmetrical alkanes? If you draw a line in very between of your alkane, it will divide the alkane into 2 equal parts. Okay, that's why we are calling that, we are saying that this Wurtz reaction is suitable for preparation of the symmetrical alkanes. Okay, let's solve an example. Example 6.7. It's saying that predict the order of reactivity of the following compounds in SN2 and SN1 reactions. So we have given the 2 choices, or the 2 sub points in this example. The first is 4 isomeric bromobutanes. And the second is C6H5CH2 bromine, C6H5CH, C6H5 bromine, C6H5CH3 bromine, and C6H5CH3 bromine. So you have given this two parts of this example, and the example is saying that you have to predict the order of reactivity of these compounds given in these parts in both the type of reactions SN2 and SN1. So you have given some time. Try to solve this question and then we will see the correct answer. Okay, let's see. So let's see the first part. The 4 isomeric bromobutanes. So for the bromobutanes, you should have to first of all know the 4 different isomeric of bromobutanes. Okay, so these are the 4 isomers of bromobutanes. The first is very simple. You have to draw a parent chain containing 4 carbons and the bromine is present at very first carbon. The second structure is you have to draw the 4 carbons, but you have to write the 4 carbons, but the bromine is attaching now with second number of carbon. Third isomer, that at your second carbon there is methyl substituent and at your first carbon we have bromine. And in the fourth isomer, you can draw the bromobutane structure as a tertiary halide where bromine is attaching with the second carbon, and also at the second carbon the methyl group is also present as a substituent. So these are the 4 different isomers of bromobutanes, right? Each one containing 4 different carbons, 1 bromine, okay, attaching at different position of carbons, and the basically they are structurally different but their molecular formula is same. That's why we are calling them as isomeric bromobutanes, right? Now, let's see for the SN1 reaction, the substitution nucleophilic unimolecular reaction. The order will be reactivity in the SN1 reaction is determined by the carbocation stability, right? So basically, SN1 reaction is a first order reaction. So it happens in the 2 steps. The first step is slow step, and in the first step, the carbocation forms, okay? So if the carbocation form is stable, its reactivity will be more, right? So in this reaction, the SN1 reaction, the reactivity is determined by the carbocation formed stability. And you know that the order of carbocation stability is from tertiary to primary in the higher to lower manner. Like tertiary carbocation is most stable, then secondary carbocation, and the primary carbocation is the least stable, right? And similar order will be for the reactivity. So if you see the compound 1 and the compound 3rd, they both gives primary carbocation. So how carbocation forms after the removal of leaving group? When the leaving group left, in the SN1 reaction, in the first step, the leaving group will be detached from the molecule, from the haloalkane, and your carbocation will be formed. The most stable carbocation will be the tertiary one. But here we are talking about the first and the third carbocation. So in the first, the bromine will be removed and you will get a primary carbocation, because bromine, when it is removed, the positive charge will come at this carbon, which is attaching with only one other carbon. In the third case, in the third compound also, when bromine is removed, positive charge came at this carbon, which is only attaching with one other carbon. So this is also a primary carbocation. So first and third gives the primary carbocation. The second compound will give a secondary carbocation because the bromine will be removed from here. So this carbon will have positive charge, and this carbon is attaching with other 2 carbons simultaneously. So this second compound will give a secondary carbocation after the removal of bromide ion. Lastly, compound 4th will give you a tertiary carbocation. When this bromine will be left, the positive charge comes at this carbon, and this carbon is attaching with other 3 carbons, right? So this is a tertiary carbocation. This will form a tertiary carbocation. Okay, and because we know the carbocation stability is the factor for determining the reactivity in the SN1 reaction, we can say that compound 4 will be the most reactive, and then compound 2nd, and then compound 1st and 3rd. But what? Let's see. So comparison between 1st and 3rd you have to do, because both will give primary carbocation. It is very clear in the 4th and the 2nd that 4th is the tertiary 4th will give tertiary carbocation, so it will be most reactive. The 2nd will give the secondary carbocation, so it will be after 4th compound. But in the 1st and 3rd you have to compare because both will give primary carbocation. So if you see CH3 whole twice CH2Br, which is actually the 3rd one, and CH3 CH2 CH2 CH2Br, which is simple chain attaching with the bromine. In these two, the first one is actually more reactive. So isopropyl group provides a greater electron donating inductive effect, which stabilizes the carbocation intermediate, and that's why it will be more reactive. So in the 1st and the 3rd compound, in the 3rd compound, if you see, the carbocation the positive charge will come on this carbon after the removing of the bromine group, the bromine atom, right? And in the 3rd compound, the isopropyl group, this isopropyl group will provide greater electron donating inductive effect, and this effect will going to stabilize the carbocation intermediate that will form in the 1st step of the SN1 reaction, due to which the reactivity of the 3rd compound would be greater comparative to the 1st compound. Okay, so after the comparison between compound 1st and 3rd, the 3rd have greater reactivity than 1st. So we can finally write the overall order between these 4 isomeric bromobutanes. The tertiary one, the tertiary carbocation, or you can say tertiary halide, is actually most reactive because tertiary carbocation is most stable. Then comes the secondary carbocation, which is your 2nd compound. Okay, and then comes your 3rd compound due to the presence of electron donating inductive effect. And then least reactive will be the primary carbocation, which is the 1st compound, which is providing by the 1st compound. Okay, so this is the overall order for the 4 isomeric bromobutanes of the reactivity for the SN1 reaction. Now, if we talk about the SN2 reaction, substitution nucleophilic biomolecular reaction, and this is a single step reaction, happens in a single step. Transition state will be formed, no intermediate formed, right? The nucleophile will attack from the opposite of the carbon halogen bond, remember? So the reactivity in the SN2 is inversely related to steric hindrance. Okay, so steric hindrance is the key factor here for determining the reactivity. So reactivity is inversely related to the steric hindrance. If there is a steric hindrance, the reactivity will be lower. If there is no steric hindrance for the incoming nucleophile, then there will be reactivity will be more. So the more substituted carbon atom attached to the halogen, slower the reaction. Okay, if your carbon halogen bond is there and the carbon which is attaching with the halogen is more substituted carbon, then the reaction rate it will show is slower due to the steric hindrance. Steric hindrance faced by the incoming nucleophile towards the carbon. So the order of reactivity in the SN2 reaction is the primary halides are more stable, then the secondary halides, and least stable will be tertiary halides because tertiary halides are containing more substituted carbon that is attaching to halogen. So if you see in these 4 isomeric bromobutanes, the 1st and 3rd are primary halides because bromine is attaching with one carbon and carbon is attaching with one other carbon. So 1st and 3rd compound are primary halides. The compound second is secondary halide, due to the same reason that bromine is attaching with carbon, which is attaching with other two carbons. And the compound fourth is actually our tertiary halide, because bromine is attaching with the carbon that is attaching with three other carbons. So here also you have to compare between the compound first and third, because both are primary. So in this case, this single chain bromine, you can say N bromobutane, okay, is more reactive. Why? The isopropyl group in this in this third structure, which is your primary halide, okay. So this isopropyl group presence hinder the nucleophile more and slower the rate, because if you see the third structure, it is a primary halide, we know, but due to the presence of this isopropyl group on this carbon, or you can say on this carbon which is attaching to halogen, the incoming nucleophile will be facing steric hindrance, due to which the reaction rate will be slower. But in the case of first product, there is no steric hindrance and the reaction rate will be greater. So the overall order now you can simply write that most reactive will be the first isomer, which is N-bromobutane. Then comes the CH3-2CH2Br, which is actually your third compound, which is also a primary halide. Then comes the secondary halide, and then comes the tertiary halide, that is fourth compound. Okay, so primary, secondary, and tertiary. This is the overall order for the SN2 mechanism. Now, let's see the second part, which is we have given the molecular formulas of the structures. So the structure of the compound will be, if you draw, the structure will be something like that. First structure for C6H5CH2Br is this. The second structure is this, where two benzene rings are attached with a single carbon, and that carbon is attaching with bromine and hydrogen. The third structure is like this, where one benzene ring is present and over which there is carbon, bromine, and hydrogen, and that carbon is attaching with the methyl group. In the fourth structure, we have two benzene rings attaching with a single carbon, and that carbon is attaching with CH3 and the bromine. So these are the four different structure of the compound of the molecular formula that is already mentioned in our second part of the question. Now, first we have to evaluate the order for SN1 reaction. So for the SN1 reaction, the reactivity is determined the carbocation stability. So we will see that the carbocation stability order is that tertiary carbocation is most stable and primary carbocation is least stable. And now we will check that which carbocation will be formed by which compound from first to fourth structure. Compound first is actually the primary carbocation. The compound second and third is actually form secondary carbocation, and compound fourth will form tertiary carbocation. Now, because compound second and third both are giving us the secondary carbocation, so we will check. So in these two, the most reactive is this one, where two benzenes are present, that is the second compound. Why? Because resonance stabilization of carbocation will happen in the second structure in compared to the third structure. In third structure, there is only one benzene ring and the other carbon is of methyl group. Okay, so there is the absence of resonance stabilization in the third compound. So the second compound will be more reactive due to resonance stabilization of carbocation, or more stable due to the resonance stabilization of carbocation due to the resonance property shown by the two benzene rings. So the overall reactivity order will be the highest for C6H5C CH3 C6H5 bromine, that is your tertiary one. Okay, then for the C6H5 CH C6H5 bromine, then for C6H5 CH CH3 bromine, and then for C6H5 CH2 bromine. Least will be for primary, that is the first compound. Okay, so this is the reactivity order which we have determined after seeing the visualizing the four structures of the four compounds given in the second part. So this reactivity order is according to the SN1 mechanism. Now, let's see according to the SN2 reaction. So order for the SN2 reactions, reactivity in the SN2 reaction is inversely related to the steric hindrance. So more substituted carbon attached to the halogen will show the reaction rates lower. So order of reactivity in the SN2 reaction is primary halide, most reactive, then secondary halide, then tertiary halide. The compound 1 is a primary halide. The compound 2nd and 3rd both are secondary halide. And the compound 4th is tertiary halide. The same step we will follow. We will compare between the 2nd and 3rd because both are secondary halide. Here, compound 2nd is less reactive than the compound 3rd. Why? Because there are bulkier phenyl group are present in the compound 2nd, which will offer more steric hindrance, or which will hinders the nucleophilic attack. So compound 3rd will be more reactive. So reactivity order will be highest for the first one because it is a primary halide. Then for your 3rd one because it is a secondary halide, but it is not having a bulkier phenyl group as compared to the 2nd one. So 2nd one comes at the 3rd position in the order, and then comes the 4th halide, which is your tertiary halide. Okay, so this is the reactivity order according to the SN2 mechanism. Let's see another example. Example 6.8. Identify the chiral and achiral molecules in each of the following pair of compounds. The wedge and dash representations are according to the concept we have seen in the class 11th. So we have the first part where part of the first part is given having different structures. Okay, the first structure have bromide and the hydroxyl group as a substituent. In the second structure, we have 2 bromide as substituents. In the second part, we have 2 structures. In the first structure is different from the second structure, like structurally. Okay, the substituent is present at the very second carbon, and in the second structure, we have the substituent at very 3rd carbon. Now, in the third part, we have again 2 structures which are differing by the position of the bromine attaching with the carbon. So you have to identify chiral and achiral molecules in these pairs. You have some time, try to solve this question, and then we will see the answer. Okay, let's see the answer. So the molecules that are having all the different substituents around a carbon, that are known as chiral molecules. And the molecules that are having symmetry or the same group is present around a carbon, that are known as achiral molecules. Okay, this is the main difference between the chiral and achiral molecules. Now, if we look at the structure in the first pair given, the first pair having the first structure is actually a chiral structure. Okay, because all the substituent attaching with this carbon are different. In the second pair, we have this compound, this structure is achiral because we have 2 same substituent as bromine. So 2 substituent are same, which is bromine. So one is chiral, another is achiral. Now, if we look at second part, we have these 2 pairs. The first one is actually chiral because around this carbon, we have 1 hydroxyl, 1 hydrogen, 1 methyl group, and other this propyl group. So this is a chiral molecule because all the substituents are different. Now, if you look at this, okay, in this structure, this carbon is having hydroxyl, hydrogen, ethyl and ethyl. So we have 2 ethyl groups around this carbon. So this is a achiral molecule because 2 substituents are same, which is ethyl. Okay, so that's why one is chiral and the another one is achiral. There is also a presence of symmetry if you look at the achiral molecules. If you draw a line at this third carbon, you can see that there is symmetry. Now, in the third pair, we have two different structures. The first structure is actually chiral due to the same reason that this carbon is having one hydrogen, one bromine, and this side it is attaching with the ethyl group and methyl group at the other side. So this is a chiral compound or chiral molecule. All substituents are different. If you look at the second product, we have this carbon attaching with bromine, two hydrogens and the propyl group. So we have two hydrogen that is same. This is a chiral molecule because two substituents are same here around that carbon at which the bromine is present. That is hydrogen. Two substituents that are same is hydrogen. So this is a chiral molecule. So one is chiral, another is achiral. So this is how you can identify the chiral achiral molecules in these given pairs. Okay, let's look at the summary. We have talked about the dehydrohalogenation reaction, which involves the removal of hydrogen from beta carbon and halide from alpha carbon. So this was the reaction we have seen. There is the removal of beta hydrogen by the attack of base, and there is removal of leaving group on the alpha carbon, and there is a formation of double bond between these two carbons. We get our product as an alkene. Then we have talked about the Saytzeff rules, which says that the preferred product is that alkene which has greater number of alkyl groups, the greater number of substituents. Good nucleophile but weak base. If there is in the reaction there is good nucleophile but the base is weak, it will favor a substitution reaction, and high temperature will favor the elimination reaction. Then we have talked about the reaction with the metals. So alkyl magnesium halides, also called Grignard reagents, the reaction of haloalkanes with these or with the magnesium in the dry ether will give you a Grignard reagent. So haloalkane react with magnesium in the presence of dry ether, you will get your Grignard reagent RMgX. And for the preparation of symmetrical alkanes, we used Wurtz reaction, where we get the product where the carbon number was double comparative to the halide which we are using as a reactant. So Rx, two molecules of alkyl halide join together and react with the sodium metal to join together as a product and give you a final hydrocarbon having double the number of carbon atom plus 2 sodium halide will be your side product. Okay, thank you so much. That's all for today's session. Thank you.